Good evening, good afternoon, ladies and gentlemen. My name is Robert Dijkgraaf. I'm since the 1st of July the director and Leon Levy professor of the Institute for Advanced Study. And it's my great pleasure to welcome you to what, for me as a director, is the first public lecture here at the Institute for Advanced Study. It's a great pleasure that we have such a distinguished speaker today. At the end of the lecture, there will be some time for questions, and then we will all go to the common room in Fould Hall to celebrate with a small reception. And there you can kind of continue the discussion. So our speaker today is Juan Maldacena, who is actually celebrating this year his 10th year as professor in the School of Natural Sciences at the Institute. Juan completed his undergraduate education in 1988 at the University of Buenos Aires in Argentina, before earning a licenciatura at the prestigious Balsaro Institute, also in Argentina, in 1991. Then he came to Princeton University, where his advisor was Kurt Callan, who is now also a much valued trustee of the Institute. After earning his PhD in 1996, from Princeton, Juan did postdoctoral research at Rutgers University, then moved to Harvard in various incarnations as a visiting associate and full professor. And in 1999, he started his relationship with the Institute, first as a member, then a visiting professor, and then in 2002, he joined the permanent faculty. Juan's work is very broad, that focuses on string theory, quantum gravity, and quantum field theory, but I think his kind of greatest distinction is that he's not only working in all these fields, he also was able to connect certain fields in a very deep way that has really influenced the theoretical physics community in a remarkable sense. Now, it's often said that a typical scholarly publication has a single reader, namely the author himself, and sometimes you even doubt that's the case. But it's a remarkable statistics that of the 45,765 papers written in the last 50 years in theoretical particle physics, Juan's 1998 paper, The Large N Limit of Superconformal Field Theory and Supergravity, received the most citations of all. I checked this morning, it was 8,555. And just to note that the second is Steven Weinberg's model of leptons, which in some sense was part of the launch of the standard model of particle physics that we will hear about. So this just shows how influential his work was. And that work was also recognized by many, many prizes. I just mentioned here the Dirac Prize of the International Center for Theoretical Physics, the Daniel Heinemann Prize for Mathematical Physics from the APS, the Sackler Prize in Physics, a MacArthur Fellowship, and this summer, Juan received also the Pomeranchuk Prize of the Institute for Theoretical and Experimental Physics in Moscow, a prize that past recipient was Professor Dyson. I guess that was all in some sense topped by the announcement this July that Juan was, among with 3 other members of our faculty, awarded the Fundamental Physics Prize. The first round of these prizes, there were 9 prizes in total, 4 of them actually received here by faculty of our institute, and each of these prizes carry an award of $3 million. So it's an exceptional recognition, I would say, of an exceptional achievement. In fact, in some sense, it was accompanied with a kind of a special kind of 4th of July firework, in the sense that we had the announcement of the discovery of the Higgs particle also in July, an effort that took more than 50 years of theoretical work. In fact, Peter Higgs, who wrote a 2-page paper, one of his first seminars on this topic was given here at the Institute in the early 1960s. And now finally, after a tremendous effort of 10,000 people working on a large hadron collider, finally led to this discovery of the single particle. And we're extremely excited that we today have the combination of the two, so to say, and have Juan talk about the Higgs bosons. And I think the title of his lecture, the symmetry and simplicity of the laws of nature and the Higgs boson, really already bears on, I think, one of the elements that we want to highlight the enormous importance of fundamental deep ideas, and sometimes the long time these ideas take to fruition, but also the enormous impact these ideas have on the world. So it's a great pleasure to announce, and I hope you will help me welcoming Juan Maldacena to this lecture. Thank you very much.
Thank you very much. It's a great pleasure and a great honor to be able to give this talk. I'll be trying to describe the theory behind the Higgs boson and behind the Standard Model. And I will not give a historical talk. I'll try to give a logical talk or pedagogical talk, trying to explain what we understand about nature today. And our understanding of nature is a bit like the fairy tale of the Beauty and the Beast. We have, on one hand, we have the beauty, which is represented here by the forces of nature, the electromagnetic, weak, strong, and gravitational forces. And they're all based on very elegant and simple principles. And on the other hand, we have something complicated and mysterious, which is the Higgs mechanism. And we really need both to understand nature. And we are, in some sense, the children of this marriage. Now, symmetry. So let's start discussing symmetry. This is a very simple concept. So we have figures that do not have particular symmetry. So here, this figure, if we reflect it along this line, remains the same. The square has many lines along which we can do reflections. We can also do rotations by 90 degrees of the square. So the square has many symmetries. And there are some figures that don't have particular symmetries. Now, there are figures like the circle or this that have this continuous symmetries and the rotation under any angle. So they are the symmetry group, or the set of all symmetries is bigger. And of course, we also have spheres that have many more symmetries. So we have a nice sphere here. We can rotate it around any axis. And the set of symmetries of the sphere is a little more complicated, because you can rotate it at one axis and then another axis, and that can give you a different final answer than rotating them in the opposite order. Anyway, so those are the symmetries that we will talk about. And they are realized in nature in an interesting way. Of course, we usually associate symmetry to beauty. That's why we are saying that the laws are, that's why we said it's the beauty part. And these symmetries we are going to talk about are in some sense hidden, and it has taken a long time to uncover them. And they are so hidden that in some sense they are not even symmetries. You could argue that they are not symmetries, but just a convenient way of describing the system. And we'll see this in a very concrete example. The objective today will be to explain these symmetries, what they are, why they are very simple, and they lead to a very simple picture for the laws of nature. And then what is the Higgs mechanism, and why the Higgs particle is necessary. Now, in nature, we have four forces, as I mentioned before. I'm only going to talk about two of the forces, the electromagnetic and the weak force, but the other two are also based on principles of symmetry, very similar to the ones that I'm going to discuss now. Okay, so let me start with electromagnetism. Of course, we're all familiar with electricity and magnetism. They are the dominant force for everyday life. They determine how atoms work. They determine chemistry, etc. And it was essentially hidden until around 300 years ago, due to the fact that positive and negative charges cancel out almost completely in ordinary matter. There are other forces of nature like gravity, which were obvious, but the force of electromagnetism was very, very subtle, and it took a long time to discover. But understanding it led to a huge amount of technological progress, as you all know. So let's start with high school electromagnetism. This is probably what you learn about electromagnetism in high school. So if we have a particle, a charged particle, and we have an electric field, so there is a new concept, which is an electric field, whose role in life is to push electric particles, or we can detect it by noticing how electrically charged particles are pushed. And we also have magnetic fields. Magnetic fields only act on moving charges. And when we have a constant magnetic field and we have a moving charge, the moving particle will move on a circle around the magnetic field. When we have a magnetic field, as I said, it acts only on moving charges. But if we go to the rest frame of the moving charge, the charge is by definition not moving, but there's still some acceleration. Therefore, there should be some electric field. So when when an observer is moving in the presence of a magnetic field, he also sees an electric field. So in other words, by going to a frame which is moving relative to another, we can turn magnetic fields into electric fields. So in some sense, and the fact that the laws of nature are invariant under this motion of frames, under constant motions, relates electric and magnetic fields. Now, electromagnetic fields, the electromagnetic field has a dynamics of its own. It oscillates and leads to waves that propagate in empty space. These waves are light, radio waves, X-rays, gamma rays, etc. Now, these equations for electromagnetism can also be viewed as based on a certain gauge symmetry. The first one to discuss this was Hermann Weyl, and he discussed it shortly after the theory of Einstein's general relativity. He tried to derive electromagnetism based on invariance under measurements or gaugings. Gauge is just something you use to measure. And his original idea was unsuccessful, but small modification of his idea really works and is a way to think about electromagnetism. And I'm going to try to describe this, this way of thinking about electromagnetism, because it will be particularly useful for the other interactions. And I'm going to try to describe to you, based on an analogy from economics, okay, a monetary analogy. So we're going to set up some rules. There are rules somewhat similar to the rules of economics, but simpler. In fact, so this is not a model of economics, it's a model of physics. And you'll see that physics is simpler than economics. So we're going to have countries. And each country will have its own currency. And when you go from one country to the next country, to the neighboring country, you need to change all your money to the new currency. Okay? You cannot take money from one country to the next. You have to change at the border, you have to change to the new currency. Okay? That's the rule of the game. In real life, you can take the money, but not according to these rules. Okay? So with these rules, you have to change to the new currency. At the border, you will have some banks that will change this money for you. They will be very nice banks. They will not charge any commission. That's also not a realistic assumption for economics. It is for physics. The banks that exist in physics are like this. But each bank will set the exchange rate it wants, so it's free to set any exchange rate it wants, and we'll later see what constraints these exchange rates have. And another assumption we'll make for now is that there is nothing to buy. We'll later relax this assumption, and you'll see that the consequences of relaxing this assumption are quite interesting. But for now, there will be nothing to buy. So very simple story. Okay? All you can do is take money from one country to the next. Okay? So let's see. So we have these three countries here. One country has its own currency, the dollar. The other one has euro. And here we have pesos. And well, we have some exchange rates. These are not realistic exchange, but some exchange rates. I put them simple just to keep the calculations we're going to do in a simple manner. So we have 6,000 pesos a dollar. So if you have 6,000 pesos here, you cross the border, you're given a dollar. You come back, you get back your 6,000 pesos. Okay, nothing happens. Very good. Now, the gauge symmetry consists in the following. Consists in each country can change its currency units. So let's say the president here decides, well, 6,000 is too much. Let's just invent a new unit. Let's call it the Austral, new monetary unit. And this Austral will be 6. So 1,000 pesos will be now 1 Austral. It's a decree. This is what it's going to be from now on. And the banks adjust the exchange rates immediately to the new monetary unit. But it's the same. Nothing changed. And even if there were things to buy in the country, if you adjust the prices accordingly, nothing really changed. This is just a simple change of monetary units. This does happen in real life. This is the example. Notice they didn't even bother to print the new money. They just put a stamp with a new denomination. Okay? And this happened many times during my lifetime. In fact, one current peso is 10 trillion of the pesos when I was born. But anyway, so it happens all the time, and nothing happens, I assure you. This is perfectly harmless. It's a complete symmetry, OK. Now let's go back to the previous example, but now I changed one of the exchange rates, OK? Notice that the rule said that the banks could set whatever exchange rate they wanted, OK? And so this bank could choose this exchange rate, and this bank this other exchange rate. But now you can see that there is some interesting things you could do with this. So if these were the exchange rates, you can go again from Argentina to the US, and if you go back and forth, you don't earn or lose any money. But look at the following thing you can do. So you can start with 4, let's say, Australes here in Argentina, then go to the US. You end up with $1 at the US, thanks to this exchange rate. And then you travel to Europe. You get €1. And then you come back to Argentina, and you end up with 6 Australes. Okay? So you earn some money. Okay, this opportunity to speculate. Now, in physics, we call this a magnetic field. We say that here, we say that there is a magnetic field here, perpendicular to this plane. Okay? And in the presence of this magnetic field, or in this situation, speculators would start going around and around and around this circuit. And that's what electrons do. Electrons just go around and around magnetic field, just trying to earn money. Okay? This is exactly what happens. Now, in real life, it's complicated. There are many countries, and you can fly from one country to the next. That's too complicated. So but in physics, it's simpler. So I told you physics was simpler. In physics, all countries are exactly identical, except that they each choose their own currency. You cannot fly from one country to the next. You just have to go through all the other countries. And you have to change your mind. You go from here to here. There is some exchange rate here. You have to go change it. Here, there is a different exchange rate. The exchange rates don't have to be the same. So here, the only complication is that for each white link you see here, there is one particular exchange rate that could be different. And so there could be opportunity to speculate. There could be, you could earn money by going around here, and the electron will go around here, and so on. So all the countries are identical. They are arranged in a grid like this. And this is all going on, presumably, at very short distances. So we have to think about this going on at very, very short distances. At distances that are so short that this even will look completely continuous. We don't distinguish these individual countries, but it looks to us like a continuum. And so this is the space-time continuum. Each country is like each point in space-time. And the electron, when it moves around, it goes between the different countries. And when it goes around them, it changes the electron currency. And if there is a magnetic field, it earns money. Okay. Now, electromagnetism is essentially the same as this, as what I've described. There is one small difference that in electromagnetism, instead of having the symmetry, instead of being a symmetry of rescaling the units of money, is simply the rotations of a circle. That's the symmetry we have at each point in space-time. So what we have is at each point in space-time, we have a little circle. It is as if we had a little circle. We don't know whether the circle is real or not. Maybe there is a little circle, there is some extra dimension, perhaps. We don't know whether there is an extra dimension. What we do know is that we have the symmetry of making a rotation. We have a symmetry which is the same as the symmetry we would have if we had this circle. But what we do have is a kind of exchange rate, which is called the electromagnetic potential. And this exchange rate tells us that if we're at this point on this circle, when we go to the next circle, we are going to be displaced. We are going to be sitting at this point. Okay? So when we have an electron sitting at this point on the circle, it moves to this other circle here. It will sit at this point. There's another exchange rate here, and so on. And in this particular situation, the electron, after going around this circuit, it will not come back to the same point. And So we have a magnetic field, and electrons really like that, and they will go around it. So that's the analogy. And again, all this is happening at very short distances. Now, in nature, we also have quantum mechanics, and so the laws of physics at the laws of physics are probabilistic, and this is manifested very clearly at short distances. And in the analogy, it's more or less like saying that these exchange rates are random with a probability distribution that depends on the opportunity to speculate. So they depend on the magnetic field. And configurations with large opportunities to speculate are less probable. So in some sense, it's like saying nature doesn't like speculation and will not offer you these opportunities very easily, but it will offer them to you if you can find them. So that's the quantum version. Now, I won't be able to describe quantum mechanics. An hour wouldn't be enough, probably, to describe all the features. And one slide is even less. But all these things end up implying that the energies of many systems are quantized. In some sense, the energy is also related to how unlikely something is. So something with high energy is more unlikely. And one of these systems are electromagnetic waves, and they're also quantized. And so these electromagnetic waves are quantized. Their energies come in quantum units. And one quantum of field excitation is what we call the particle. So we have a picture where we have all these exchange rates. We can excite them, but these excitations come with discrete, in some sense are discrete. And these excitations, we call them particles. So there is, in quantum mechanics, there is this correspondence between these excitations of fields and particles. This is something I'm not explaining. I'm not explaining it with the analogy. You have just simply to accept it. So sometimes we'll talk about particles, or you hear people talk about particles, and they are this simplest field excitation you can have in quantum mechanics. Okay, so with all this, we can have the theory of electrodynamics. It's based on this gauge 3 symmetry I mentioned, symmetries of rotations similar to the symmetries of rotation of a circle at each point in space-time. It leads to a massless photon for a reason we'll see later. And the electron is massive. And the nuclei and electrons, plus all their electromagnetic interactions, explains most of what we see in everyday life. It explains atoms and so on. Okay, so that's electrodynamics. Now we have weak interactions. Now, weak interactions are important for certain radioactive decays. For example, if you have a neutron that is outside the nucleus, it can decay into a proton, an electron, and an antineutrino. And this decay is mediated by a very massive particle called W boson. Now, these weak interactions are very important for historians because of, for example, carbon-14 dating. It's based on the weak interactions. And the weak interactions, though they are weak and maybe not important for everything, not important for building iPods and so on, they can move mountains. Indeed, radioactive decays hit the Earth, and the Earth moves. This heat produces convection inside the Earth, moves continents, and forms mountains. Okay, all thanks to weak interactions in part. Now, the weak interactions are based on a gauge symmetry. And in this case, the gauge symmetry is the symmetry we would have if we had little spheres at each point in space-time. So these little spheres could be 2 extra dimensions with the form of a sphere. We don't know whether that's what is behind this, but what we do know is that when we go from one point in space-time to the next, we need to specify 3 quantities, which are similar to the 3 quantities you would have to specify if you have to say how this sphere is rotated relative to the other sphere. Okay? So 3 quantities, you could think of them as the angle of the axis of rotation and then the angle of rotation. So those are the 3 quantities you need to specify when you go from one point of space-time to other points in space-time. So what we don't know is that we need to specify these 3 quantities, whether it's due to the fact that there is a little tiny little sphere. We don't really know. But we have these 3 variables, and in the quantum theory, it leads to 3 weak so-called gauge bosons. These are similar to the photon, but associated to the weak interactions. And this gauge symmetry of the weak interactions, if all we have are these are similar to the exchange rates we had before, except that now we have these three quantities. And just this gauge symmetry determines the interactions among all these particles and determines completely the theory, again in this continuum limit I discussed before. So this is a theory that was written by Young and Mills. And when Young gave a seminar here at the Institute, Pauly was in the audience, and he objected very strongly that this did not make any sense. His theory did not make any sense, because those gauge bosons, according to his theory, would be massless. Okay? So this really looked like another beautiful theory killed by an ugly fact. Okay, okay, so let's try to understand better why we had these massless particles. And this can be understood a bit by understanding the energies of waves. Okay, imagine we are comparing two different waves which have, let's say, the same amplitude, but one has a wavelength which is which is shorter than the other wave. Okay, so and this, for a reason we'll see in a moment. So if these are electromagnetic waves, we'll see it in the next transparency. We'll have more energy than this one. So the fact that the particles are massless is related to the fact that in the long wavelength limit, these waves have very low energy. Okay? Compare that to massive particles, which even for when the associated wavelength is very long, that would be when the particle is not moving, then the energy according to Einstein's formula would be equal to the mass. Right? So whether the particle is massless or not depends on whether the associated wave at very long wavelengths has low energies or not. So let's go back to this situation of exchange rates, and I'll try to explain why, with the rules we have set, the energies of long wavelength excitations have less energy than the ones with short wavelength. So we go back to this configuration of countries, and we'll focus on 4 of them at a time. By choosing currencies appropriately, we can set all these exchange rates to 1 and all the exchange rates along these horizontal lines to 1. Okay? I mean, we can start with one country here and then go to the next and change the currency of this country so that the exchange rate is 1, and then we can repeat. And so all of those could be set to 1. And now let's consider this configuration. So we have here an exchange rate of 1 to 1 in going from here to here. And in going from here to here, we have an exchange rate of 1.1 to 1. Okay? So in this situation, there is an opportunity to speculate here. Okay? Now, we could still make a transformation here where we exchange the currency of all the bottom countries to, let's say, 3 times their value. And in that case, the exchange rate would be 3 to 1 and 3.3 to 1. But it's clear that the opportunity to speculate is fundamentally the same. Okay, nothing really changed. So because all we did was this change of currencies along all the bottom links. So what we see is that the opportunity to speculate is independently of the magnitude of this exchange rate, whether it's 3 to 1 or 1 to 1 or 10 to 1 or whatever. Right? What is important is how much this exchange rate differs from the next exchange rate. Okay? Now, what is a wave? So a wave is a situation where we have, again, all the countries. I've now magnified the whole, well, or made it smaller. And we can have a wave like this or a wave like this. So this wave, what it means is that the exchange rates along the vertical links, sorry, I didn't draw the vertical links, but the exchange rates along the vertical links are oscillating. Sometimes they are 3 to 1, sometimes they are 1 to 3, etc. But in this situation, they are oscillating much more rapidly. So they change much more when we go to one country to the next than in this situation. In this situation, they change very little when we go from one country to the next. So I hope it's clear that the opportunity to speculate in a given circuit is much smaller in this situation than in this situation. Okay. Okay. So the end of this story is to say that a very long wavelength configuration gives you little opportunity to speculate, and that's essentially the reason that the photons are massless. And that was essentially Pauli's reason, except that It was even simpler because he expressed it in the language of mathematics, and that language is simpler to explain these things. Now, how do we solve this mass problem? And what comes to what saves us is the beast, the Higgs mechanism. And this is an idea that was developed by many people. And the idea is basically that there is an object that is sitting at each point on these weak spheres. So before we had these little spheres, it would be like having an extra dimension. But now we have the extra dimension, and we have an object sitting at some point on these extra dimensions. So that's one physical realization. What we know is that there is something that puts a distinguished point on this sphere. So that's what we know. We don't really know whether these spheres are real or not. But what we do know is that there is some substance that transforms or changes when we make a rotation. Okay, that's what we do know. And this exists even in the vacuum. So this is even in the vacuum in empty space, there are these little spheres, and there is this point, this special object sitting there. Now, let me go back to the monetary analogy. Okay? So now we'll go back to the monetary analogy, and we will assume that there is something to buy in each country. Okay? There is one thing we can buy. Let's say that gold. So we can buy gold in each of the countries, and we can take it from one country to the next. Okay? And gold will have some price in each of the countries. The prices are again set by each country. In each country, they decide whatever price they want for gold. And now let's consider this situation, which is similar to the one we considered before. Notice, first forgetting about gold, notice there is a magnetic field here, as there was before. But now we also have gold. And now there is a new opportunity that presents itself for us. And it's the following. So before, when there was no gold, by going back and forth between these two countries, we wouldn't earn or lose any money. Okay? All we could do is take money, and we wouldn't earn or lose any money. But now notice something we can do. We can start with $1 here. We come here. We start with $1. We buy gold. Okay? We take the gold to Argentina. We sell it for 6 Australes. Now we come back here, and we get $6. Okay? We started with $1. After this whole operation, we end up with $6. Okay? So now we can speculate by going back and forth between these countries. We don't need to do all this whole circuit. Just back and forth between countries, we can earn money. Okay? Now, one thing we could do is we could just choose the currency units in all the countries in such a way that the price of gold is 1. So here we did a change of currency units in Argentina, so we're used to these changes, and it doesn't matter. And we called it the P. So 6 of the previous units are now 1. 6 Australis is 1p. And so now we have we adjusted these two exchange rates. We adjusted the exchange rate of the price of gold. So now the price of gold is the same in all the countries. And so now we use this freedom to choose the currency units by fixing the price of gold to 1. And now immediately we can see that if any exchange rate is not 1-to-1, we can speculate, we can earn money by going back and forth between these countries. Okay? So for example, here now in the new, this is called fixing the gauge. And when here, since the price is 1-to-1, we don't earn or lose any money by going back and forth here, and either whether we take gold or we take dollars, etc. We don't earn or lose any money. The same here. But here, if we go between Argentina and the US, we will. Okay? And so there is a preferred exchange rate. So after we do this, there is a preferred exchange rate here, which would be 1-to-1. Right? Before, there wasn't quite a preferred exchange rate, but now there is one, which is the exchange rate that does not allow you to earn money. And as I was telling you before, nature doesn't like to offer you opportunities to speculate. Okay? So the laws are such that this will cost you some probability. So in some sense, it's less probable to have this link having this value than this link being 1-to-1. Okay? So it's less likely that you find it in this configuration. Or another way of saying this is setting this link to this value will cost you some more energy. Now, so without gold, the exchange rates between two countries were arbitrary. Only comparing nearby countries could we speculate. We wouldn't earn any money just going back and forth. Now, with gold, the exchange rate between two countries has this preferred value. And you can speculate by just going between two neighboring countries. And the fact that there is a special exchange rate at which you cannot speculate is related to the fact that the gauge bosons will have a mass. So before, we had this configuration where some exchange rate, for example, was 3 to 1, and there was no problem. But now, after we have this Higgs, we input the price of gold, set it to 1. If we have any exchange rate which is 3 to 1, we have a big problem. So we will not have, so the energies of configurations will be, a long wavelength will be independent of the wavelength and will be non-zero. And so that will lead to a mass for the gauge bosons. So there is something called the Higgs field, and which in this analogy is the price of gold in each country. And once you set that to 1, or once you set that to a constant value everywhere in space, then this leads to a preferential value for the exchange rates, and this leads to the masses for the weak gauge bosons. Now, these masses imply that while the electromagnetic interactions are quite long range, or the weak interactions are very short range. And the reason is that, again, it's related to this fact that we can create long wavelength excitations of the electromagnetic field without much cost in energy or much cost in probability. And that enables electrons to interact with each other even if they are not too close to each other. While for the weak interactions, the particles really need to be very close to each other because otherwise it's extremely improbable to produce these weak gauge bosons. And for that reason, electrons that go through our body, that hit our body will interact strongly with it, while neutrinos that are just passing through us, emitted from the sun, just go through us and don't interact with us almost at all. So the mass of the weak gauge bosons explains the weakness of the weak force and explains why the weak force has remained. Well, this explains why it's not relevant for everyday life and why there is electronics and not neutrinonics, for example. Now, so this explains how the Higgs mechanism gives the mass to the weak gauge bosons. But the weak force has other strange features. And before describing those strange features, I need to talk a little bit more about rotations and rotations. Let's start with rotations in space. So objects in space can rotate. And I said that in quantum mechanics, the energies of many systems are quantized. And the energy contained in a rotation, let's say, is quantized. Or the amount, even the angular momentum of the rotation is quantized and comes in integer values. And an elementary particle can also rotate, and they can carry these minimal amounts of rotation, small amounts of rotation. And one way to understand this is to notice that we can have a circularly polarized electromagnetic wave. I wonder why. Well, anyway. These were supposed to be moving, but they are not moving. So we can have circularly polarized electromagnetic waves where the electric field sort of rotates around the direction of motion or direction of propagation of the wave. And they can rotate in one direction or in the other direction. And we represent that as saying, well, let's say the green arrow is the direction of motion of the wave. And if it's rotating in one direction, we draw another arrow in one direction. Or if it's rotating in the other direction, we draw the arrow parallel to the direction of motion. So there are these two circularly polarized waves that we can have, and this corresponds to two, when we quantize them, we have a photon with two possible circular polarizations. Or this is sometimes also called spin. So the photon is somehow spinning around the direction of motion. Now the electron also has spin. So if it's moving, it can be along the direction of motion or the opposite direction. If it is at rest, it can also have the spin or small amount of angular momentum. Now, there is one interesting surprise. The weak interactions depend on the spin of the electron. And the weak interactions are stronger when the spin is antiparallel to the direction of motion of the electron. Now this is a bit surprising for the following reason. For massless particles, we can distinguish particles depending on where the spin is in the direction of motion or in the opposite direction. So as we just said for the photon, right? So we have a particle propagating this way, and the spin can be in the direction of motion in the opposite direction. For massive particles, this is not quite possible because we have the particle at rest and we have the spin, and we don't have any direction of motion in any other direction in order to distinguish one spin from the other. Let me say that in a different way. So imagine we have an electron that is moving, and it has a spin pointing in this direction. So this observer would say that this electron has the spin in the direction of motion. For this observer, the electron is at rest. It cannot say in which direction the spin is pointing. And this observer is moving even faster and will say that the spin of this electron is in the direction opposite to the direction of motion. Okay? Now for light, that doesn't happen because light travels faster than anyone else, and you cannot catch up with light. And so for light, once the spin is in the direction of motion, nobody will see it in a different direction. But for electrons, this is not possible. Okay, so this is a problem. So now let's pretend the electron is massless for the time being. So again, this is a problem similar to the problem that Pauli suggested to Young. And let's first forget about this problem and pretend for a second that the electron is massless. Then what happens is that for the weak force, there are two types of electrons. There are the electrons, which we can call left-handed, where the spin is opposite to the direction of motion, and the ones we are going to call right-handed, where the spin is along the direction of motion. And since now we assume the electrons are massless, they are always moving, and we can really distinguish between these two cases. And in one case, this electron is not really doing anything in the weak sphere, in these two extra dimensions, if you wish, while the other electron is really rotating in this weak sphere, and it has one minimal unit of angular momentum on this sphere. And it's rotating in one direction, but it could also be rotating in the different direction in the weak sphere, and that's another particle, which we call the neutrino. So again, the spin in the opposite direction, and the only difference between the left-handed electron and the neutrino would be simply that they are rotating in different directions on the weak sphere. And if we didn't have the Higgs field, we could have the weak interactions, and this would be the whole story. Now, in order for this to work, I noticed here that there is no neutrino that looks like this one. Or at least certainly. Okay, so what Li and Yang realized while being here at the Institute was that this implied that the laws of nature are not symmetric under a mirror reflection. And the reason is that if we have a neutrino, which is, let's say, left-handed, and we look at its image in a mirror, so it's moving this way, in the mirror it will be moving this way, and this one is rotating in this direction, but the mirror reflection would be rotating in the other direction. So the mirror reflection will look to us like a right-handed neutrino. But well, we said that there was no right-handed neutrino. And even if there was a right-handed neutrino, it would have different properties, or for example, in the case of the electron, they have different properties under the weak interactions. And this was not consistent with the mirror reflections. So Li and Yang realized that the weak interactions were breaking parity. And we now understand exactly how parity is broken. So the laws of nature have many symmetries, but parity is not one of them. So if there was no Higgs field, we would have something very simple. We would have electromagnetism and the weak force, both based on this simple gauge principle. And we would have essentially two types of particles. One is the right-handed electron, and the other is these two other particles, which are essentially like only one, because these two only differ by how they are moving in the weak sphere. The strong interaction can be added in a similar way with the quarks. I'm not going to discuss that very much. So this is very simple. All particles are massless. Everything is based on symmetries. And the strength of the interactions would be fairly similar. Now here I cannot resist showing you this picture. Now, in the old days, people used to discuss the celestial spheres and make models of the universe based on various spheres and symmetries and so on. Now we continue to do the same thing, except that the number of spheres has gone up by a huge amount. We have one sphere per point in space-time. Okay, going back to the talk, so we need to explain the electron mass. And the idea is that it is due to the interaction with the Higgs field. So the idea is essentially the following. So we had the left-handed electron, which is coming here. It is rotating on the weak sphere. But as it rotates in the weak sphere, it could interact with this little object that was there and kind of transfer the spin to this object and come out as a right-handed electron. Okay? And so these left-handed electrons can interact, left and right-handed electrons together interact with the Higgs field. This is like a new force of nature. The strength of this interaction will be related to the electron mass. And so if this happens, when, let's say we have the vertical direction here is time and the horizontal direction is space, we have, let's say, a left-handed electron. So we have this electron which is moving to the right. This line represents the fact that it's moving in time. And it has the spin in this direction as any good behaving right-handed electron does. So the white are the right-handed electrons, and these light blue ones are the left-handed ones. So notice that here it interacts with the Higgs field. It becomes a right-handed one moving in the other direction. Notice the spin is opposite to the direction of motion. And then it interacts again. It moves to the right, and so on. So basically what we end up having is in quantum mechanics, we can have a superposition essentially of these two states, the left and right-handed electrons. And depending on how much we have of each of the two, the electron will have a net motion, which will be less than the speed of light. So it will be less than this 45 degrees, which would be the speed of light. Will be moving less. If it had equal amounts, it would just remain stationary. And if it has more of the left-handed electron, it will be moving to the left. And if it has more of the right-handed electron, it's moving more to the right. So if it has more of the left-handed electron, it will interact in a stronger way with the weak interactions. There is more purple here than there is white. If it's moving a lot to the right, then there will be mostly white, and it will not interact very much with the weak gauge bosons. Now, this interaction explains the mass of the electron, and the mass of the neutrinos can be explained in a similar way, except that we have neutrinos interacting with antineutrinos and the Higgs field. Now, this is sometimes called the electroweak theory, and the final form of this theory was written by Salam and Weinberg. And so in this theory, we have the symmetries of the circle, plus we start with this gauge principle with the symmetries of the circle plus the symmetries of the sphere. And the symmetry of electromagnetism is really a combination of the circle and the rotation of the sphere. And that's why the electron and the neutrino have different charges. So the circle we start with in the electroweak theory is not directly the circle of electromagnetism. The circle of electromagnetism is a combination of these two. And the fact that the neutrino and the electron carry a different spin in the weak direction, the weak sphere, is why the electron and the neutrino have different charges. So the mechanism we have discussed explains the masses of all particles and the weak gauge bosons and so on, but it does not predict the existence of a new one. Okay? It does not predict the existence of the so-called Higgs particle. This explained all the features of the standard model before the announcement this July of the discovery of a new particle. Okay? Now, what would be the Higgs particle? So in the monetary analogy, the Higgs boson, the one that was discovered, would arise when there are two objects we can buy in each country. Let's say we can buy gold and silver. Okay? And the relative price of gold and silver, as we go between different countries, the relative price of gold and silver is really the Higgs boson. Okay? So once we set the the price of gold equal to 1 everywhere. If there is any variation in the price of silver among countries, we will have opportunities to speculate, again going among neighboring countries. And so that type of excitation, for the same reasons I discussed before, would be massive. And so this ratio would behave as a massive particle. And that's the new particle that we expected that should exist. But why do we need at least 2? So theorists were convinced that with just only 1 it would be a problem, and we had to have at least 2. So why did people think that? The reason is quite subtle and has to do with the possibility of taking the limit when distances between countries become very small, and in a way that interactions at long distances remain finite. So it's the same process we discussed before, and if we did it with the weak interactions with no extra particles, no Higgs boson, we would find that the theory in the continuum would become totally trivial. Okay? So we knew that before July 2012, we definitely knew that from theory that there had to be new particles with masses below 1,000 GeV. So that just for mathematical consistency of the theory. And the Higgs boson was the simplest possibility. And there certainly were many others, thanks to the prolific imagination of theorists. And so how are we exploring the breaking of electroweak symmetry? So in order to explore it, we need to collide particles to very high energies to produce this predicted new particle, this predicted Higgs boson. Okay? We have to collide things at high energies because it's very unlikely to have this fluctuation, let's say, between the price of gold and silver we discussed before, since it's a massive particle. And for that purpose, this collider was built, this Large Hadron Collider in Geneva. And this works very similar to how small electron colliders work. Now, you're probably very familiar with the small electron colliders, and you've spent lots of time looking at them. This is just a TV, okay? So a TV is a small electron collider. But these are the old TVs. Maybe if you now have liquid crystal TVs, the principle is slightly different. But it has a beam of electrons coming from the back, hitting the screen, and producing photons, producing light that you see with your eyes. Okay? Now, the LHC works with essentially the same principles, electric fields pushing particles, with the small difference that for a TV, maybe you accelerate an electron to 8,000 volts. But for the LHC, you go all the way to, all this big number. 8 trillion. 8 trillion volts. So the LHC gives them 1 billion times more energy than an ordinary TV. So a strategy would be to get to this energy, to put 1 billion TVs one after the other. That's called linear collider. And it would take the distance from here, more than the distance from here to the moon. So that's not the strategy that was. So you might think that the LHC is large, but it's not as large as if you were to make it with TVs. So it's a circle, and we have these magnets that making particles go around the circle. And hadron means fat, okay? And so a proton is a fat particle that collides. And since it's fat, produces lots of noise. We have protons colliding, and each time they collide, they produce a shower of particles. The shower of particles they produce is different each time they collide because of quantum mechanics. So the result of the collision cannot be calculated a priori. There is probability of, you can calculate the probability that different outcomes will happen. And each time you do the experiment, different outcomes definitely do happen. And since we have a lot of energy available, we produce many particles. And this shower of particles, though looks complex, is determined by these very simple gauge symmetries we discussed in the beginning. In particular, the gauge symmetry for the strong interactions, which I didn't discuss too much, but is very similar to what we discussed. Instead of a sphere, we have the symmetries of complex projective two-dimensional space, if you know what that is. So they built these huge detectors to detect this shower of particles, our experimental colleagues. This is a person. This one is called Atlas, and here you see it holding the weak sphere in front. I don't think that's what. This is a picture when they were assembling it. And so protons collide and produce many particles. Very rarely, they produce Higgs bosons. And these Higgs bosons decay very quickly into other known particles, leaving a special imprint that then is analyzed. So for example, Higgs bosons could decay into 2 photons. So it's a situation where perhaps a Higgs boson was produced here and immediately decayed into 2 photons. And if you essentially sum the energies of these 2 photons, you have to do something called the invariant mass, but roughly speaking, it's like summing the energies. If it came from the decay of a Higgs boson, it should give you the mass of the Higgs boson. Okay? Now, there are many other things that can produce 2 photons. As we said, in the case of the Small Electron Collider, or the TeV, when the electrons collided with the electrons that were in the screen, they produce photons. In the same way, these protons or quarks, when they collide, they can produce photons. They can produce 1, 2, 3, 4, etc. photons. But if you take pairs of them, so you look at events that produce only pairs of photons, and you sum their energies, in general, the sum of these energies could vary more or less randomly and would be more or less uniformly distributed according to this dotted line here and solid line in between. Okay? So this graph is saying, so if these are all events of 2 photons, and let's say the sum of the 2 photons energies is 100 in some units that are useful for this, which are called GeV. They observed, summing over all the events, they observed, well, considering all the events they had, they observed only 1,800 events that had 2 photons, summing to an energy of 100 GeV. And so on, they produced this plot. And there is this little bump here, which is concentrated around 126 GeV. And we think this little bump is due to the decay of the Higgs boson. So the decay of the Higgs boson produces 2 photons with precisely 1 energy, which would be its mass. So this bump gives evidence for the Higgs boson, and in addition, it's telling us what the mass of that Higgs boson is. So theorists had predicted that there should be at least 1 new particle with mass less than 1,000 GeV, and indeed they found one at energy 126 GeV. Okay? Now people ask sometimes, what is this useful for? Now I have to be honest, I don't know of any technological application of this. Now here, there is the apocryphal quote of Faraday, who when asked what the possible technological application of electricity was, he said to the prime minister, someday we will be able to tax it. I think maybe we could say the same thing about the Higgs boson. But something we do know is that it is helping us understand what happens in nature at very short distances. We are finally understanding how the electroweak force really works at short distances, and those seemingly contradictory things we need to assume for the electroweak force, it actually all works out, and we have a consistent theory for the weak force. And now what? So now there are reasons to think that there will be new particles. There are not reasons that are as strong as, new particles that will be detected at the LHC. One reason, there is an essentially theoretical reason, which is really a question. Why is the mass of the Higgs so small compared to the Planck mass, which is the mass scale of gravity? And then there is an experimental reason, which is the fact that we observe dark matter. So these 2 things hint to the possibility of detecting new particles at the LHC. Now dark matter, we know from astrophysical observations that there is more matter than the one we see. So if we look at the sky and we see some galaxy sitting there in the sky, surrounded by what looks like the blackness of empty space. However, so that's what we see. But what we can measure by doing detailed gravitational measurements is that there is some distribution of matter, which basically will look like this. So it's extended much bigger than the size of the original galaxy. And all this is a theoretical simulation. Actually, it was done by some ex-astrophysicist members here at the Institute. And So we have definite evidence of this from astrophysical observations, so this particle probably exists. However, what we don't know is whether this dark matter particle will or will not be produced at the LHC. So there are some theories in which the dark matter particle will be produced at the LHC. But in any case, there are other experiments looking for dark matter in other ways. But something that is clear is that thanks to the LHC, there will be more exciting experimental discoveries in particle physics in the first few years. And we'll eventually finally understand how they lived happily ever after. So how the weak interactions and the Higgs field or fields or whatever it is works and gives us the nature we live in. And Nima will talk on the Higgs and the future, and especially what we expect for the future in his talk on Friday, October 26th at 5:30 p.m. Thank you.